So I wanted to talk with you a little bit about the background of the Wittig reaction, and that's experiment 31 in the manual that we're currently using. The Wittig reaction was discovered not all that long ago, speaking, back in the 1950s. And the faculty, or I should say the scientist who discovered this, George Wittig, or Georg Wittig, he actually ended up winning the Nobel Prize for this in the 1979 is what it was. So this is an extremely important reaction. And the main reason why, or one of the main reasons why this is so useful to a chemist, is because we can take a carbonyl compound, specifically an aldehyde or a ketone, and using a Wittig reagent, right, we can transform that into a carbon-carbon bond. So we can swap the oxygen in our carbonyl for another carbon that's bound to a, whatever it could be there. It could be some more alkyl groups or hydrogens or whatever it might be. So we can basically click together, right, two different carbon chains under the right conditions and change an oxygen in a carbonyl for a carbon. And so we can swap a carbonyl for an alkene. So we're going to talk about what the mechanism is for this, and then we're going to actually use a Wittig to prepare a diene. Now, generally speaking, this is going to be a 2-week reaction. In the first part, we're going to prepare a Wittig reagent, which is, in our case, going to be a quaternary phosphonium compound. Okay. And what we're going to do is we are going to take triphenylphosphine, right? So triphenyl, 3 phenols, phosphine plus benzyl chloride, and we're going to quaternize our phosphine compound. So I'm going to abbreviate this here. Okay, so we have 3 of our benzenes, and then we add our benzol group on there. Okay, so quaternary phosphonium. Remember, phosphorus is right underneath nitrogen on the periodic table, and so we have similar reactivity between phosphorus and nitrogen. In this case, we're going to quaternize that phosphorus compound to make the beginnings of our Wittig reagent. Okay. So that's the first thing that we're going to do. Then we're going to take our compound here, right, and we're going to react this with cinnamaldehyde to prepare a diene, right? And so we'll look at the 2 mechanisms that are going on in both of these parts A and part B here, okay? Now we're going to learn a new skill. It's called thin layer chromatography. Now thin layer chromatography can have 2 purposes. Its most common purpose is as a qualitative analysis for how many compounds are in a reaction. And we can use that idea, that qualitative analysis, to see how far along our reaction is, meaning is the reaction complete or not, or how many different things we have to purify or separate to get our compound out of a reaction. We'll talk about how to prepare prepare thin layer chromatography and how to analyze it. Old skills, or I should say, or reinforced skills that we'll be using is how to set up a reflux, and as usual, NMR and IR to kind of analyze our data at the end of it. So let's discuss thin layer chromatography. Now, generally speaking, thin layer chromatography is used for the qualitative analysis of a mixture. And so what's going to happen is we're going to put a little bit of our reaction mixture onto a TLC plate, a thin layer chromatography plate. So TLC, right, a TLC plate. We're going to run that TLC plate, and it's going to tell us qualitatively how many different components there are in our mixture. Now, generally speaking, TLC can tell us a couple of things, and we're going to be using it to see how far along our reaction is proceeding. Now, what I mean by that is, so as you begin a reaction, you know that there's going to be certain components in there. You can run a TLC plate to see where your starting material is, and then as you go along, later on you can run another TLC plate, and if you see another spot show up, or if you see a spot move further, then that's an indication that some reaction is happening and something's going on. But remember, it is a qualitative analysis, okay? So let's talk about how this actually works. So when you go into lab, what you're going to do is you're going to get a aluminum piece of aluminum piece, and on that aluminum piece you're going to have a white coating that's going to be silica gel. So we're going to have silica gel on top of a aluminum coating. Now this is going to be our solid phase, and it is extremely polar. Well, maybe extremely might be a bit much. Let's just say it's very polar. Okay, so you're getting an aluminum piece of rectangle, like an aluminum rectangle. It's got silica gel in the front. That solid phase is extremely polar. What you're going to have to do then is prepare a chamber for the TLC, which is either your jar that has the screw-on lid or a beaker with a watch glass on top of it. So you're going to get your chamber. All right, so let's draw a little chamber here. Okay. And into that chamber, you're going to put some solvent. I believe for this lab, it's going to be petroleum ether. So this is our mobile phase, and it's nonpolar. Okay, so mobile phase, that's nonpolar. So maybe you can start to see where this is going, right? We've got a polar solid phase and a nonpolar mobile phase. And it's going to be that interplay between the polarity of the two phases that's going to help us separate the components. So let's talk a little bit about how we actually prep our TLC plates. So let me just erase that to clear it up. Okay. You're going to have a line at the bottom of your TLC plate. And let's say that you're going to put a spot of your reaction solution onto that line. Okay, so we're going to spot our TLC plate. You want a concentrated sample, and you don't want to make a huge spot. It's going to take a little bit of practice. It may or may not work the best the first time you run this, but don't worry about it. It's the first time you're doing a TLC plate. Okay. Now, what you're going to do once you spot your TLC plate, I can't draw this, but I'll try and show it as best I can. You're going to take your TLC plate and you're going to set it into your chamber, and you kind of want to lean it against the edge of the chamber. Okay, you kind of want to just lean it at the end of at the edge of the chamber, and you want to make sure that your solvent stays below the line that you made. Okay, so you kind of want to lean in your chamber, make sure your solvent is below the line that you made. All right, so imagine we put that in there. Okay, let me just clear up some stuff here because I'm going to have to write a little bit. Now what's going to happen is when you put that TLC plate into your chamber, because of capillary action, your solvent is going to start to rise up your solid phase. Okay, so your solvent is going to rise, and you want to make sure that you leave your TLC plate in the chamber until the solvent is almost at the top. Do not let the solvent get to the top of the TLC plate. Okay, now let's say we're trying to separate this purple. Okay, we're trying to separate that purple dot that we have there. What's going to happen is the components in your mixture, your purple mixture there, are going to interact more with either the polar phase or the non-polar phase. It just depends, right? It just depends on what you're trying to separate. And so what's going to happen is you're going to start to see distinct dots for the different components of your mixture. They're going to travel different distances on your TLC plate. So if we start out with that purple, it's going to start to rise up, and hopefully you're going to see a separation into the red and the blue, right? And that's how we're going to tell how many different components there are in our reaction mixture. Now we're going to have to visualize this with a UV lamp, right? Because not all of the components that we're going to be separating are visible, in the visible spectrum. So UV lamp's going to help us to visualize where those dots actually are. So what you're going to do, like I said, you're going to put your TLC plate into the chamber. You're going to let the solvent rise till almost the top. You're going to pull it out. You're going to let it dry out, and then you're going to visualize it with the UV lamp. So you're going to turn on the UV lamp and stick your TLC plate underneath there, and your spots are going to show up. And then you're going to mark them, okay? So when you're using the UV lamp, mark your spots with a pencil, okay? All right. So now what is this actually going to tell us, or what can we do with this? Well, typically what's reported with a TLC plate is what's known as an RF factor. What you're going to do is, using a ruler, you want to measure the distance to the solvent front. So from where you started to the solvent front. That is how far the solvent actually traveled. And let's say that this is 4 centimeters, okay? What you're going to measure then is how far each component ran. Let's say that one ran 1 centimeter, and let's say that this one ran 3 centimeters, okay? To report an RF, all you do, so RF for the blue, it went 3 centimeters out of the total 4 that the solvent front was. So you just do 3 over 4, so 0.75 for your RF for blue. And for red, you do the same thing, except 1 centimeter over your 4, 0.25. Okay, so don't forget to record and report your RF values for each of the components in your reaction mixture. So let's discuss the mechanism for part A. Remember, part A is where we're actually making our Wittig salt, right? We're making our quaternary phosphonium salt that we're going to use for part B. Now remember what we're going to be doing, or actually before I say that, let's do some abbreviations. So pH, right, is phenyl, right? So if we just have a benzene ring directly bound to something, right, a phenyl ring. Remember, we're using triphenylphosphine, right? So we got a phosphorus and 3 phenols coming off of it, okay? We're taking this plus benzyl chloride, okay? This plus benzyl chloride, and we're going to do the reaction with this. So what reaction is going to happen? Well, we got to review a little bit of our first semester organic here. Let's take a look at our halide. We got a primary halide. It's a pretty good leaving group, not the best of the halides, but not a bad leaving group either. So we'll call it decent leaving group. Okay, primary halide, decent leaving group, not overly sterically encumbered, so not too bad with the sterics. Okay, not great, but not too bad, right? It's not a tertiary leaving group, right? It's a benzylic leaving group. So if we have our primary halide, it's a decent leaving group. We're not really too concerned about sterics, right? This is all kind of pushing us towards SN2, right? But remember, we have to look at both sides of this to kind of make that decision. So over here with phosphorus, what we have a neutral leaving, or excuse me, a neutral nucleophile. Right? It's not charged. It's got a partial negative, right? Slight partial negative. It does have a lone pair, right? But it's a weak, right? It's a weak base, right? Weak nucleophile. Okay, so weak base, a weak nucleophile, primary halide, decent leaving group, not too much about sterics. This is kind of all pushing us towards SN2. Okay, so there we go. Let's do an SN2, the easiest of the mechanisms, so to speak. Send our lone pair to hit that carbon. We make a bond to that carbon. We break the bond to the leaving group. And we do a reaction. Let's bring this together. There's our phosphorus. We make a bond in red to our carbon there. Okay. Abbreviate this, pH, 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 plus here, Cl here. And then let's just fill that in red, and then we're good to go. Okay, so there it is. All right, we're doing a simple SN2 reaction, kicking off our leaving group with our phosphorus that's coming in. Okay, so let's look at the mechanism for part B. This one's going to be a little bit longer. There's a couple more steps that we have to go through with this. Now remember, we're going to be using our compound that we use in part A, or excuse me, the compound that we made in part A to complete our Wittig reaction. And so we've got this guy here, right? Our salt, our phosphonium salt. Now the first thing that we need to do is that we have to generate our Zwitter ion. Now Zwitter ion just is referring to an ion that's got the positive and the negative charge within the same molecule. It comes from the German for zwei, for two, right? So it's Zwitter ion. So all we're going to do in this case is we're going to put in a strong base. And for our reaction, as we're reading through our notes, it tells you guys to use sodium eth oxide. So if you're looking through the book, it tells you guys to use sodium eth oxide. We're going to do a slight change and do sodium meth oxide. Okay. How's that going to change the reaction? Not much at all. Right? How's it going to change your procedure? Not much at all. The only difference is instead of using, I believe they tell you to use 3 milliliters, we're just going to be using 1.5 milliliters. Okay? So just make a note of that in your changes here. So sodium meth oxide is going to come in. It's going to deprotonate those acidic hydrogens, the benzylic hydrogens, right there. Okay? All right, let's see what happens after this first one. I'm going to abbreviate this by putting my pH in, pH 3 there. Okay, there's that, there's that. And let's put a black dot right there, okay? So let's put a black dot on that carbon because I'm going to be referring to that carbon specifically there, right? So now we've got our deprotonated Wittig salt there, okay? Now remember, if we want to boil down organic chemistry, right, it all comes down to, organic chemistry comes down to something negative attacking something positive. Now I'm going to simplify this and I'm just going to put in a generic ketone, okay? So there's a generic ketone. Remember, for our case, we're going to be using an aldehyde, cinnamaldehyde. So one of our R's is going to be equal to an H. Well, it's going to work the same way in the mechanism at least, okay? So, mechanistically, let's look at this. The negative attacks the positive. Negative attacks the positive. Okay? Negative attacks the positive. The negative ion that we just made attacks the positive carbonyl carbon, kicks up the pi bond. So pH 3 there, right? There's our black carbon. There's our benzene ring. Let's see if we can fit this all together. In purple now, we've got a bond to our green carbonyl carbon. That's bound to an oxygen and our 2 R groups. And plus here, okay? So our lone pair on that black carbon got turned into a bond to the carbonyl carbon. Now we're going to clean this up a little bit here, right? What's going to happen next is that our negative is going to attack our positive, but this time the negative oxygen there in green is going to attack our phosphorus. It's going to make a weird, well, I shouldn't say weird, it's going to make a unique 4-membered ring, okay? So negative is going to attack positive like this. So let's sketch this out. It's going to take a little bit of work. So let's put my phosphorus there. It is bound still to my black carbon. Got it, okay? Which is bound in purple to my green carbon. Okay, green carbon. Pardon me, I'm still fighting a cold here a little bit. Green carbon is still bound to a oxygen in green, which is now bound to my phosphorus. Okay, so this is what happens with that arrow, with that step there with the red arrows. Now we just got to fill in the blanks, so to speak, what's left over. Fill in my 2 R groups, and then here we've still got my phenyl ring. Pretty complex. All right, now we've got another set of arrows that we got to deal with. So what's going to happen is the bond between the phosphorus and the black carbon is going to go and turn into a pi bond between the 2 carbons there, while this bond between the carbonyl, or what was the carbonyl carbon and the oxygen, turns into a pi bond between the phosphorus. So phosphorus we made our first bond, we made our second bond to our oxygen. Oops, let me just clean that up, sorry. That didn't come out very clean. pH 3. Plus, right, now we broke that ring apart. So we got our green carbon here. That was our carbonyl carbon. We made the purple bond earlier. We added the white pi bond, right, in that last step to my black carbon, which now has, which still has my phenyl ring on it. Right? And don't forget that there is still, remember that we had an understood hydrogen here from the beginning, okay? We never lost that hydrogen, we just haven't put it in yet, but there it is, okay? So there is the mechanism for a Wittig reaction. We generate a negative, right? We generate a negative carbon here, right? We generate a negative carbon there, which attacks the carbonyl carbon. The negative oxygen then attacks the positive phosphorus to make a four-membered ring. And the four-membered ring kind of snaps shut to generate a phosphorus-oxygen double bond. And phosphorus-oxygen double bond, there's a very stable bond, which means it releases a lot of energy when you make that bond, which is kind of one of the driving forces behind why this reaction even goes. Okay? So here's the generic mechanism with that. Hopefully you guys can follow along. So in summary, take a note of the change in the procedure between sodium meth oxide and sodium eth oxide. Review your TLC concepts, the thin layer chromatography, both in this video and what it's written in your procedures in your lab book. Don't forget how to set up a reflux and your NMR and IR. I know at this point in the semester you guys have been doing this a lot, so hopefully you guys remember how to make the proper samples. Okay, use clean glassware. Going to be very important when you guys are running through this reaction. Make sure everything's nice and clean. Okay, so make note of these changes, review your stuff, and you will be all set to go into lab.